Hello guys, welcome back to video 2. In this video, I want to talk more about hypothesis tests, and maybe explore some more of the nuances of the pieces that make up a hypothesis test. It's kind of a big topic at first, and maybe it's hard to take it in all at once. So let's review some of the details about the 4 steps of a hypothesis test and what they're for and how we use them. Remember, confidence intervals and hypothesis tests are 2 big forms of statistical inference. Think to yourself, what is statistical inference? Statistical inference is the process of making conclusions about a population based on sample data. And there are 2 main ways that people do it: confidence intervals and hypothesis tests. Keep in mind, confidence intervals are used for estimates. In other words, they answer the question, what is it? What's going on? What is the population parameter? We do confidence intervals when we have no idea what's going on and we want to investigate. On the other hand, hypothesis tests are used for answering a question about a population parameter. We have a specific suspicion or claim about a population, and we want to see if there's evidence to support us in the sample data. Maybe a common application might be in a medical trial, for example. Suppose that some people are taking a new medication and another group of people are taking a placebo. We might wonder if there's evidence of a difference in the effectiveness of those 2 treatments. And a hypothesis test is designed to answer a question like that. We saw last time that there are 4 important pieces of a hypothesis test, and I want to think about those again. Let's really think about all of those pieces. Oh, just as a reminder, of course, please feel free to pause when you're watching these videos. There's a lot of text on this screen. You might want to spend some more time reading it than it takes me to talk about it out loud. First, let's talk about the first step, hypotheses. Every hypothesis test has 2 competing hypotheses: the null hypothesis, H0, and the alternate hypothesis, HA. We need both of these things. They're always logical opposites of each other. So one of them's got to be true. We always set up these tests so that the 2 competing hypotheses are logical opposites of each other. If one's false, the other one's got to be true. The null hypothesis is the assumption that we're making about a population. And for that reason, the null hypothesis is always a statement of equality about a population parameter. All of those words are super important. Let's think about this in the context of a specific example. How about, maybe let me make up a weirder number just so 0.34. Let's say, for example, the null hypothesis, H0, is P equals 0.34. Everything there is super important. In the stuff that I'm highlighting, nothing can be omitted from our description of the null hypothesis. Literally every symbol there is absolutely crucial when we're doing a hypothesis test. First, we're saying H0. In other words, we're defining what the null hypothesis is. Next, we're clearly stating what population parameter we're talking about. We've already seen that there's lots of different parameters out there: mu, sigma, p in this case, and others still. So we need to say for sure, okay, what quality of this population are we talking about? In this case, in this made-up example that I just gave, we're talking about p, the population proportion. Next, equals, also super important. Every null hypothesis is going to have this same form. We're making a statement of equality about this parameter. In other words, we're being honest about our assumptions here. We're saying upfront, okay, assuming that the population proportion is blah, here's how our work unfolds. It's always going to be an equals in the null hypothesis. If not, you're doing it wrong. And then, of course, we need to say specifically what value we're assuming it to be. This is really important. We need the null hypothesis to compute both the test statistic and the p-value. These probabilities that we're computing, they're not magical. We can't just, poof, conjure them out of thin air. We have to make some assumptions about the population in order to do these probability computations. And that's what the null hypothesis is all about. Being honest about our assumptions that we're using to perform the test. Next is the alternate hypothesis. This one's also really important. Now, it's always the logical opposite of the null hypothesis, but it's a little bit more than that too. The alternate hypothesis is our claim or our suspicion about what's going on. In the context of a criminal trial, it's guilty. And the whole reason we're doing this test is because we, the investigators, we think that the alternate hypothesis is correct. We're hoping to find evidence that it's correct because that's the assertion that we're making. And since it's always in the form of some sort of change or difference, the alternate hypothesis is always a statement of inequality. In other words, it's got to be one of these three things. It's either got to be less than, greater than, or not equals to. This exclamation mark right here that I just highlighted, that's not equals to. In software, we use exclamation marks to mean not. So that literally means not equals to. If I was writing it on the whiteboard, I would do an equals with a slash through it. So as an example, how about I'll keep this one the same. As an example alternate hypothesis, we might wonder if there's evidence that the proportion is actually less than whatever the null hypothesis said. Keep in mind, these two numbers here, whatever the actual value is, that's always going to be the same in both the null and alternate hypothesis. These things I'm highlighting, that actual number part in both the null and alternate hypothesis, those are always going to be the same. In the null hypothesis, we're clarifying our baseline assumption. In the alternate hypothesis, we're telling what we hope to prove. Since only one of these things can be true, we're hoping to find evidence to support this one. Okay, test statistics. Test statistics are, of course, statistics. Like any other statistics, it's a summary of our data. So, for example, if we're talking about proportions, sample proportions, our test statistic is always going to be a z-score for the sample data. And we've seen how to make z-scores for proportions. Again, go back to week 8 and look at the forwards problems if you're forgetting this formula. This formula right here, this is exactly the same thing. That's not new. We did that in week 8 when we computed probabilities in forwards problems for p-hat. So this tells us this is a single number that summarizes what's going on in our sample results. And one thing I want to mention here, all of these occurrences of p, here's one here, oops, sorry, here's a p, and here's a p, and here's a p. All of those occurrences of p, those are the value, those are all the same value that's in the null hypothesis. Whatever the null hypothesis said, that's going to be the same value here in the test statistic. This first one, p hat, that's the sample result. That's our observed. Everything else here is going to be p. All of these are the things that come from the null hypothesis. It works a little bit different than in confidence intervals, because in confidence intervals, we don't have any idea what p is. We're not making any assumptions about p in a confidence interval. In fact, the reason we're doing a confidence interval is because we're hoping to show something about what p is. Here, in a hypothesis test, we're making an assumption about the population value. That's step one. That's the null hypothesis. So we'll use that everywhere in this formula. In short, this is the formula for z-scores for proportions. Later on, when we do hype tests for means, we're going to see a different test statistic, but it's still going to be a z-score. It's just going to use all of the different parts from the sampling distribution for x bar. So it's going to be x bar minus mu over sigma divided by the square root of n. Still a z-score. Still exactly the same thing that we did in week 8, but using the mean stuff. That's going to come next week. We're not going to do that this week. Let's do it next week. Just here's a little heads up for next week. Okay, next, p-value. Remember this definition. It's so important. A p-value is the probability of observing a sample result that's as or more extreme than the one we got, assuming that the null hypothesis is true. In other words, we got the sample result. How likely is it? How likely is it to get a sample result like the one we got? What's the probability of this sample result happening? Of course, in order to compute that probability, we need to make some assumptions about the population, and that's what the null hypothesis is for. We can't find any of this stuff without the null hypothesis. But to actually find these probabilities, we're using the z distribution, as always. Well, we might use the t distribution too for means later. But either way, we're going to be looking for tail area in the test statistic. These are just the same thing. Let me emphasize here, exactly the same as forwards problems for p hat and x bar. This part is just like doing a forwards problem. Do keep in mind, it could go either way. Sometimes you'll be looking for the area of the tail on the left, and sometimes you'll be looking for the area of the tail on the right. And that's your left, that's your right. I gotta think about it, it's backwards. Oh, as long as I'm thinking about backwards things, you know what time it is? Oh yeah, it's time for the answer to secret video question, the only secret video question for week 11, video 2. The answer to secret video question for week 11, video 2 is bubble bath. I love bubble bath. I like taking bubble baths. I've been using Mr. Bubble bubble bath since I was 2 years old. And it's been my favorite bubble bath ever. Mr. Bubble. He and I have had a lot of good times together. Bubble bath is the answer for secret video question. The secret video question for week 11, video 2. Sorry, I'm getting confused now. Okay, back to p-values. You can always tell which direction you need to look at. It's stated specifically in the alternate hypothesis, left or right. If the alternate hypothesis has a less than, that means you're looking on the left side. if the alternate hypothesis has less than, then your notion of extreme is smaller. You're looking for evidence that it's smaller. So that's over on the left side. On the other hand, if your alternate hypothesis has greater than, that means you're looking for bigger values. Those happen over on the right side. Maybe just as a quick example, in this made-up hypothesis that we looked at earlier, we had less than. So this is going to be a left tail test. We're looking at the area on the left side. And that really matters because, let me bring up your z-table. Remember, the z-table always shows you left side. You can see in the picture. The z-table always shows you left side probabilities. So if you're doing a right tail test, if your alternate hypothesis has greater than, that means you're always going to need to do 1 minus. So it's easy, there's not much work to do, but keep that in mind. If you've got a right tail test, that's always going to be 1 minus. If you've got a left tail test, then just use whatever values in the table. And lastly, we need to make a conclusion. It's pretty simple to do, but there are a lot of important nuances to consider here. The short story is, if our p-value is small, then that means, according to the null hypothesis, the data that we observed is unlikely. Think about that for a second. P-value is the probability of getting a sample result like the one we got, according to the null hypothesis. So if that probability is small, it basically means that the null hypothesis and our data disagree. So in that situation, of course, as empiricists, in other words, we make our conclusions based on our observations, we're going to go with our observations and we will reject this hypothesis. If p is small and the null hypothesis says that reality is unlikely, of course we're going to go with reality. We're going to reject the null hypothesis. And that means, specifically, we have evidence to support its logical opposite, the alternate hypothesis. Remember, when I say small, that's what that alpha thing is for. This whole alpha part, that doesn't come into play until step 4. Alpha isn't used until step 4. It's specifically our standard of proof. How small is small? That's what alpha is all about. It's called the significance level. Alpha equals significance level. It's how small this p-value's got to be. And we don't really do any math with it. We just check. Is our p-value smaller than alpha? We use alpha equals 0.05 by default. So if a problem ever doesn't state what alpha should be, you can safely assume that it's going to be 0.5, 0.05. We might use other values for alpha in certain contexts, though. It's a really interesting topic. We're going to talk about that next week. Now, on the other hand, if we've got a large p-value, if our p-value is bigger than 0.05, then we're going to fail to reject the null hypothesis. In that scenario, we didn't find the evidence that we're looking for to support the alternate hypothesis. And that's kind of a bummer. We have sad feelings as investigators when that happens. Remember, the whole reason we're doing this thing is because we're hoping to support our claim. We're hoping to find evidence that the alternate hypothesis is correct. But if we get a large p-value, that didn't happen. If we get a large p-value, the null hypothesis and our data agree, we don't have any reason to throw out the null hypothesis. And that means we don't have any reason to support our claim that we were making. So, I kind of think of that as a disappointing end to a hypothesis test. We're hoping to find a statistically significant result. And that was a lot of words, but to really break this stuff down, every hypothesis test in the whole world always ends in one of two ways. Every hypothesis test has one of two possible options. We're going to do a whole bunch of work here, but in the end, it's going to be one thing or the other. If p is small, we reject the null hypothesis. And that means we found strong evidence to support the alternate hypothesis. Yay! Hooray! We're happy. Our claim has been validated. On the other hand, if the p-value is large, then we fail to reject the null hypothesis. We didn't find enough evidence to support our claim, and we're kind of bummed out. We're going to have to try again. Really important note in terms of your work as students. When you write these conclusions, it's always got to have two sentences. When you write these conclusions, there's always got to be two sentences. There's two things to say, no matter what, every time. First, you need to say whether or not you rejected or failed to reject the null hypothesis. That's got to be in there. Either p is small so you reject, or p is large so you fail to reject. But also, you need to say something about the alternate hypothesis because that's the whole reason we're doing this test. Either you did find evidence to support the alternate hypothesis, or you didn't. And really, in some sense, this sentence is the most important part of the entire test. That's really the conclusion we're interested in because that was the whole reason we're doing it in the first place. For another example, I picked a textbook problem and I modified it slightly. I want you guys to try this on your own. I'm going to post the full solution in my notes here, but I'm not going to do it in this video. I want you to think about this and try this one on your own. I'm going to talk about it a little bit with you to emphasize the idea here. So here's what the problem said. I changed it just a little bit, but it's basically the same. The problem from the book on page 205, 532. It is believed that nearsightedness affects about 8% of all children. Note that that's a proportion, by the way. In a random sample of 194 children, 21 of them are nearsighted. Conduct a hypothesis test for the following question. Do these data provide evidence that more than 8% of all children are nearsighted? I'm going to let you do this test, but let me give you a few pointers first. The problem gives us some sample data. It tells us that of the 194 children, 21 of them are nearsighted. If you ask your calculator, you'll find that that's 10%. 10.8%. Okay, so in other words, in this sample, yes, more than 8% of children were nearsighted. But, and here's the big but, does that mean that the whole population proportion is bigger than 8%? Remember, this is just a sample of 194 children, but there are millions of children out there. Does this sample result give us strong evidence that the true proportion of all children who are nearsighted is greater than 8%. That's the big thing that's going on here. And that's what the hypothesis test is designed to answer. By the way, I just verbalized the alternate hypothesis. Let me say it again. The alternate hypothesis is we suspect that the proportion of children who are nearsighted is greater than 8%. That's what we're testing. That's enough for you to write both of your hypotheses, null and alternate. You've got enough information here to compute your test statistic and your p-value. And you can make your conclusion. This problem doesn't state alpha, but you can assume that alpha is equal to 0.05. Try this one on your own first. Try to work it out as fully as you can before looking at the solutions. And then after you've gotten as far as you can, check out the solutions. If you did the same thing that I did, you're good. If not, you'll need some more practice. And I really want to emphasize, if you're feeling confused about this stuff, if you're trying this on your own and you're not getting these steps, you need to get help. You need to come talk to me in office hours. It's really easy for me to make up new examples and to find out the mistakes you're making. I can't do that unless you come ask for help. So don't just feel confused. Get help. All right, well, that's it for this video. Try out the problem. See you next time.